Okay, so I think we should go ahead and get started. I'd like to welcome everyone to the first Solutions That Scale seminar here at UC Irvine. My name is James Bullock. I'm the Dean of the School of Physical Sciences. And as you will soon hear, Solutions That Scale is an initiative that brings together folks from all over campus as well as the community and the broader world to talk about solutions in the realm of climate and the environment. Our first speaker of this series is, I think, the perfect person to kick this off, Professor Steve Davis from the Department of Earth System Science here at UCI. And Steve has been, I think, one of the primary architects of what we're doing here with Solutions That Scale. Steve got his PhD in 2008 from Stanford in geological and environmental sciences. He holds a JD from Virginia School of Law at the University of Virginia, and also a BA in political science and philosophy from the University of Florida. He came to UCI in 2012 as an assistant professor, and fairly recently was promoted to full professor. And so we're excited to have him here, both in the School of Physical Sciences and at UC Irvine. And with that, Steve, I'll let you take over.
Thanks a lot, James. Yeah, and it's really an honor, I think, to be the first seminar under the banner of Solutions That Scale. I'll be talking today about a bunch of different work that we've been doing on net zero emissions energy systems. And I think that will tie very nicely to some of what we mean by Solutions That Scale. But I did want to take a minute to talk about this initiative that James mentioned. So for nearly a year now, a group of faculty at UCI has been working together, meeting virtually every week to discuss what we could do as a university to bring together not just researchers, but stakeholders and business leaders and so forth to really address some of the global environmental problems that are out there. And the way I think of it is, that solutions to global environmental problems like climate change exist, but they're not always obvious or straightforward to implement. And that's because both the problems and the potential solutions are complex. These are multidimensional issues that differently affect the people out there in the world. And those people in turn have different interests and concerns and priorities, and too often these days lack trust in each other. So what we've done, and this so far is involving folks from not just the physical sciences, but the School of Social Ecology, the engineering school, public health, and computer science. We're talking with each other and trying to figure out a way to make an initiative that can build bridges among researchers with different interests and expertise, as well as stakeholders in the community and the business world and the policymakers. And really our fundamental goal is to facilitate globally actionable science. That's where the scale comes from, that it's something that can happen at global scales, but also inspire broader trust in that science. So that's all I'm going to say about it now, but you're going to be hearing more from us in the coming months. And if you're interested in learning more or getting involved, please visit our website and you can do that. So with that, I'll turn my attention to the topic of the day, net zero emissions energy systems. And I think, a lot of us have now heard this term net zero being bandied about more and more frequently. I wanted to take a minute to talk about that. Why net zero and what is net zero mean? And it really, in my mind, comes down to this plot that's from the IPCC's last big assessment report in 2014. And what you're looking at here is a plot that shows how much temperature increase we should expect in terms of global mean temperatures as a function of, on the x-axis, cumulative CO2 emissions in the post-industrial era. And what you're meant to see, there's a cone of uncertainty, but most of these are lines. The black is what's happened historically, and the different colors are telling us what might happen under different scenarios. But the fact that they're lines tells you that really every molecule of CO2 that we're adding to the atmosphere is another tiny increment on the global thermostat. This is why net zero matters, because we need to stop adding CO2 to the atmosphere in order to stabilize global temperatures. The net is because it may not mean that we've completely eliminated CO2 emissions to the atmosphere, but there may be ways of balancing the scales such that if we do have to add CO2 to the air, we're taking out the same amount on the other end to maintain the cumulative and thus stabilize the climate. And so the problem that we're all well aware of is that we still rely heavily for our energy globally, but also in the US and even in California on fossil fuels. This is actually showing on the same x-axis proven fossil fuel reserves of different types around the world, just to get at the fact that these proven reserves are ones that, at least at current prices, we could make money on if we extracted them from the ground. And they're plenty to get us towards 4 degrees of warming. So well more than some of the international targets of 1.5 or 2 degrees. So this is the fundamental challenge. The good news is that, in the last 10 years or even the last 5 years, we've had tremendous progress along the lines of solar energy, wind energy, battery technologies and electric vehicles, as well as, we have things like hydropower shown here in the lower right that we've been using for a long time to generate electricity without CO2 emissions. These all add up to meaning that there are clear pathways on how to drastically reduce the amount of CO2 emissions that we're producing now and rely less and less on fossil fuels. But there are some modern energy services that we expect will be much more difficult to fully eliminate emissions from. And so, although that progress is there and we have a path on how to drastically reduce our emissions, this talk is going to make the claim that it's time to now focus on those harder pieces of the energy system and figure out scalable solutions that can work for them. So in particular, I'll spend the rest of the talk focusing on 3 different areas of energy and energy services that are going to be tough. So the first is aviation and long distance transportation. And the second is industrial materials. And in particular, things like cement here or steel are things that are going to be a little more tricky than just light duty vehicles or something. And then lastly, we have those solar and wind technologies that are going to go a long way to getting us to carbon-free electricity sector. But we need to figure out how we can completely eliminate fossil fuels from that sector and still maintain high reliability. And so I'll spend some time talking about that. So before I get into the details of each of those areas, I wanted to note that there's actually a substantial quantity of emissions each year that are coming from those more difficult pieces. And this pie chart here shows all the global fossil fuel and industry emissions of CO2 in 2014. It's not a lot different today. But the extended pieces of this pie are those that are in these categories that I've just mentioned that I think are going to be a little more difficult. So we have in the orange some of the transportation sector, aviation and shipping, and some of the longer distance road transport. Down in the blue and purple are some of those industrial materials I mentioned. In particular, those slices of the pie are just the process emissions. I'll say more about that in a minute, from iron and steel and cement. And then the red is what we call load following electricity. So the stuff that right now, at least, is associated with following variable demand for electricity in our economy. And the point is that, it's not the lion's share of the total, but it is a large amount. More than 9 billion tons of CO2 are from these tough parts of the energy system. So almost a quarter of global emissions in recent years. So let's start by talking about aviation and shipping and some of the longer distance transportation and freight. Fundamentally, what makes these tough is energy density. So just to give you a little background, gravimetric energy density, or what we call the energy per unit of mass of something like coal, is about 20-25 megajoules of energy per kilogram of coal. When you get to refined oil products like gasoline, you've almost doubled that. So you're at 42, 46 megajoules per kilogram of those fuels. In contrast, things like lithium ion batteries are still super low. So we're at less than a megajoule per kilogram of the best lithium ion batteries today. This is telling us something about why it may be fine to have a light duty vehicle with a lithium ion battery pack that doesn't necessarily need a lot of range, but why it may be really difficult to fly a jumbo jet across an ocean with a battery powered airplane. We could also think of energy density in terms of its volume. So hydrogen, because it's a gas, has enormous energy per unit mass. You see that 143 megajoules per kilogram. But when you start thinking about the volume, that gaseous state means that it takes up a lot of space for the energy. Of course, you can compress gases, but when you do that, you need to build containment, steel tanks and things like that weigh a lot and can withstand that pressure. And so you compromise the gravimetric energy density. But this is why gaseous fuels are a challenge for even transportation like aviation as well. So in contrast, jet fuel, more than 3,000 times the energy per liter. So all of this is to say why when we're using fuels to go a long way and haul things, we may need these high energy density liquids. Just as a back of envelope to illustrate it, a Class 8 truck like this can often go 700 miles on a fill up of diesel fuel. If you tried to do that with lithium ion batteries, given the current energy density of those batteries, that same range would mean the batteries would take up about a third of the space in this truck and about 40% of its payload capacity. This should tell you why this is a challenge, that at that point, you're nearly hauling the batteries as much as you're hauling whatever else the truck is meant to be carrying. So this is not to say that it's impossible to electrify trucks like this. In fact, there are a number of companies that are pursuing that. It does mean, though, that we need to think carefully about developing systems that can depend on trucks, for example, that don't require such a large range or have modular battery packs that we can swap out, or perhaps are hybridized with fuel cells in order to offset some of the requirements of space and weight in the battery packs. So what I'm here to say, though, is that I think for things like aviation and shipping, we may need liquid fuels with high energy density for a while, if not for a long time. So to think about that, how do we do net zero emissions, but yet have these high energy density liquid fuels? There are possibilities. So here, I'm going to build out this schematic over the rest of the talk. We have our demand for these different long distance applications here at the top. And in purple, I'm representing some hydrocarbon, so jet fuel or diesel. It is possible to get that kind of a high energy density hydrocarbon without having a net addition of CO2 to the atmosphere if the CO2, the carbon in that hydrocarbon, has come from the atmosphere recently. So this is one of the reasons that people have long been interested in biofuels. The idea there is that the growing plants have taken that carbon dioxide out of the atmosphere recently, such that when we turn it into a fuel and burn it, we're just restoring that carbon again. Now, obviously, there's a lot of assumptions there that you can do this process of making the hydrocarbon, digesting that biomass in a way that doesn't involve any fossil carbon. And of course, the timescales are also an issue. If these are trees that take decades to grow, then we would be worried about burning them instantaneously. So there's also an issue with biofuels. We're going to be competing for land with feed and food crops, as well as land that we would love to leave available for nature, of course. So some prospects, but also concerns on the biofuel side. The other option for a net zero emission hydrocarbon would be synthesizing our own hydrocarbon. But again, in this case, we're going to need to think of ways that can't involve any other CO2 emissions from fossil fuels. So as a starting point for both of these options, we need to have some way of energizing the processing, the manufacture of the fuels that doesn't rely on fossil fuels. So some source of non-emitting electricity, and I've shown some here in green. In the case of synthetic fuels, if we want to make our own hydrocarbons, we need a source of hydrogen that's not fossil. And so this is where electrolysis comes in. We can use some of the electricity that we've gotten from a renewable technology, perhaps, and split the water to make the hydrogen we need for a synthetic fuel. And then, of course, the other piece of that hydrocarbon that's tough is the carbon, which, as I said, has to have come from the atmosphere. And so direct air capture of CO2 that goes into this process is one way that we could imagine making those synthetic fuels net zero. It's also possible we could capture carbon dioxide that's being produced by industry in a process, and I'll say more about that in a little bit. Just to round out other options, we could also divert, instead of making a hydrocarbon, divert some of the electrolytic hydrogen to make ammonia. And actually, liquid ammonia can be burned, has relatively high energy density. Some of the farming equipment in the United States actually burns ammonia. It's not necessarily the most attractive from the standpoint of the chemical itself being dangerous and possibly NOx emissions, but it is something that we could look into. And then further off in the future, there are folks here at UCI, like Jenny Yang, who's interested in the prospect of making fuels directly from solar energy. And this is something that's been proven in the lab. It has a long way to go before it could be commercialized. So a lot of those options you saw, whether it was ammonia or the synthetic hydrocarbons, really rely on having electrolytic hydrogen. So I wanted to spend a moment to talk about that. Right now, most of the hydrogen we use in our society comes from the process called steam methane reformation of natural gas, of methane. And that process entails CO2 emissions. So we're taking the carbon off and letting it out into the atmosphere. And it's a fossil source of carbon. So it's not a climate friendly one, but it can produce hydrogen at about $1.50 per kilogram. Unfortunately, right now, the options of taking a renewable source of electricity and using an electrolyzer to make that hydrogen in a more climate friendly way is considerably more expensive. So really the cost of electrolyzers are a major barrier. Right now, we're upwards of $4 if you factor in the average cost of electricity and the current electrolyzer costs. So we have a lot of progress to make, and folks like Jack Brower in engineering are actively working on this and very optimistic about the ability to drive down the cost of this electrolytic hydrogen in the future. But this is a big priority. So the takeaways on the topic of aviation and long distance transport are that these high energy density liquid fuels are probably going to be necessary for some time to come, and perhaps always for things like international aviation. The current options for making those fuels without adding CO2 to the atmosphere are limited in the case of biofuels, where we're worried about land area, and or costly when we think about the current costs of hydrogen production by electrolysis. And as I said, that's why making electrolysis is a real priority. So I'm going to shift gears and talk for a minute about industrial materials. And in particular, as I said, I'll talk about cement and steel. Roughly 8% of global CO2 emissions is related to cement. And that actually belies the fact there are two different sources of CO2 from cement manufacture. About half of those emissions are what we call process emissions. And they're the CO2 that come from this process of calcination. So to make cement, we heat up limestone to 1300 degrees C, and that leaves us with this calcium oxide or lime, and it drives off CO2 from the calcium carbonate of the limestone. That's the process emissions, and it's about half of the total, the other half being the energy, which is usually fossil fuels, coal or natural gas. So even if we're successful in coming up with ways of getting that high heat without emitting CO2, maybe we come up with electro heaters, we're still going to have to contend with these process emissions. And the story is similar for reduction of iron ore. We can get some amount of our demand for steel from recycling materials and electrifying the process, but to the extent we need to reduce raw iron ore, that process at least today, uses something called coke, a form of coal. So there are ways of changing these processes, for example, using hydrogen as the reductant to avoid the need for coke in the process. And that would be a way of avoiding some of the process emissions from the steel. So if I come back to my schematic, and here I've added the demand for industrial materials at the top, what I've just said is that we may have options of coming up with alternative processes. We could also think about being more efficient. And I've swapped in this plot just to show that right now, at least in the last 15 years or so, we haven't made a lot of progress worldwide at using less cement and steel in our economies. In fact, in advanced economies like the US, we use about 1 kilogram of steel and cement per person per day. So you're obviously not using that yourself directly, but it is being used on your behalf. So we could think about also driving down the demand for some of those materials might be a really important way to avoid emissions. And then I've added this link to perhaps use electrolytic hydrogen for things like steel. So we're drawing in our diagram. But the other option that gets talked about for cement and steel and industries like those is to capture the carbon that's produced from those processes and then either use them for something that would store that carbon out of the atmosphere or store that carbon out of the atmosphere perhaps underground, so CCUS. And those are options that may be important in the near term. So some work that my group has done is actually looked at this reverse process to calcination, something called carbonation. And it's something that structural engineers have known about for a long time, that when you have cement in place, it does take up ambient CO2 from the atmosphere over time, and it reforms that limestone. This isn't necessarily a good thing. As you see in the picture here, it changes the pH of the concrete and actually can lead to corrosion of reinforcing metals. But it is a good thing from the climate perspective, because the work we've done at least show that of the total process emissions over this long time period from 1930 to 2013, we think actually all of the cement out there that's been soaking up ambient CO2 has offset perhaps as much as 45% of the process emissions in recent years. The reason I take this aside is that this is another option for trying to reduce or avoid the addition of CO2 to the atmosphere. If we can come up with processes that accelerate this carbonation process, we can offset some of the emissions that are happening when we make cement. So to summarize on the industrial materials, we need to come up with fossil-free alternative processes for making these materials over the long haul, and ones that can avoid some of those process emissions. In the meantime, as I just mentioned, we can also pursue options for making and managing waste of cement, for example, that could accelerate that carbonation. And eventually, if we're able to capture and store process emissions from, say, the making of cement, then as the cement goes out in the world and is soaking up CO2, that's actually a source of negative CO2 emissions, which could help us on the climate front. So I'm going to spend the balance of my time talking about electricity. As I've said here, we need highly reliable electricity in our system. The sort of specifications for the US are that we can have a few hours of outage every decade. So we really like a high level of reliability. It's important, especially for some of our industrial activities. And so how do we get that in a system that's heavily reliant on variable sources of electricity like wind and solar? So the answer is that we're going to need some combination of flexible generation, or what we might call dispatchable generation, as well as maybe some demand management. So these are the flexible sources, could be things like nuclear or hydropower. Demand management, the idea is, well, if we don't have as much electricity being generated in a given moment, perhaps there are ways that we can manage our demand in order to turn down that demand and balance the system that way. And there are opportunities there, as well as storage. And so by now, I think most people think of storage and they think of lithium-ion batteries, which is one option. There are other things that we do to store large amounts of energy, things that are looked at like hydro, where you pump the water uphill when you have the power and let it out later, compressed air storage, or even some forms of thermal storage like molten salts. So all of these things are on the table to help us balance the variability of wind and solar. So some work we've done is actually looked at the variability in the US here. What you're looking at is 36 years of data over the entire continental United States. The variability of solar production, or it's not actually production, it's the available solar energy over the entire country if we wanted it. How much that changes in the course of a year and the variability over the 36-year period. You can see the yellow solar is obviously peaking in the summer months. There is some variability there, but it's actually quite small compared to the purple line here, which is the wind, where you see an opposite seasonal pattern of wind is tending to be higher in the winter months, and it dips, especially in the late summer, but it's very variable over the course of a year. So this shows that wind and solar can be somewhat complementary in terms of wind taking up the slack in the winter time and solar covering us in the summer. And that's why some mix of these things are probably going to be ideal. In this study, we set up a simple analysis where we assumed that we were trying to rely exclusively on solar and wind energy. And we looked at how much of the time could those technologies meet demand in the United States under different scenarios. So in this first panel, what I'm showing you is if we build a system of somewhere between 100% solar at the top and 100% wind at the bottom and some mix in the middle, but we're only building exactly enough of these capacities that over the course of an entire year, they're generating exactly the amount of electricity that's demanded in a year, but not necessarily in the same hour. And this panel also shows you the effect of if you extend the geographical scope of your system. So you can try to pack all of your solar and wind turbines in a very small area, like something the size of the District of Columbia, or you can spread it out over the entire continental United States at the right side of this plot. And the contours and colors are showing us what fraction of demand is being met. So in this first case, I should also say this is where there's no storage being assumed. So we're not able to store any of this electricity. But we can see that if we wanted to get to the highest possible level with this setup, we would want more wind than solar by a 3-to-1 margin. And we'd want to spread that wind out over a large area. And we could maybe meet demand upwards of 70% of the time. If we add the ability to store 12 hours of mean electricity demand, you see what happens is, first of all, you get more reliable. Obviously, we're going to be able to store stuff. That'll help us. But you also shift the mix away from a wind-heavy system and into a more solar-heavy system. This is because with 12 hours of storage, you're able to overcome night, essentially, the diurnal cycle of solar generation. You can also see that you can do high reliability, or at least into the 80% at a smaller geographical scale. So you don't need to spread things out as much. And in fact, I think this is an interesting thing to point out, that at some point, the US and other economies for that matter may need to make a decision whether to pursue a system that's more reliant on wind and transmission over large areas, or more reliant on solar and dependent on considerable amounts of storage. These are sort of two different options. We can also, and I'll add these panels at the bottom, overbuild our system. So we can build enough that over the course of a year, we actually get 150% of our demand for the year. And that helps us out hour to hour. You see with that system and no storage, we're still wind heavy, but we're into the 80% of power demand that can be met by solar and wind alone. If we have the storage and we've overbuilt, this is where we start getting to pretty high levels of reliability just from those. So 95+% of the time. Now, I need to point out that 12 hours of storage may sound very reasonable to everyone listening, but in fact, that's a tremendous amount of energy storage. Right now, we only have perhaps an hour or two of storage in total in the US. And 12 hours, if we wanted to get that much with lithium ion batteries, for example, would be about 150 years of production from Tesla's biggest battery, the factory, the Gigafactory. So this is a very large amount of energy storage, even though it may not sound it. And one thing that yeah.
Hey, Steve, can I just ask a quick question there?
Sure, yeah.
I seem to recall earlier discussions that even if you wanted to do that, there may not be enough lithium on Earth to do it. Is that correct?
Yeah, I think that's under some debate. It's not actually something I've looked at myself, but I've heard some interesting talk lately that there are new places that we could get lithium from, including around the Salton Sea, believe it or not, that may have considerable amounts that are untapped. So I'm not sure the answer to that question, James. But regardless, I think we have a challenge in terms of just the magnitude of trying to get to that level. Yeah.
Thanks.
So I wanted to point out, though, that even in this system that I showed, that we have overbuilt our system and we have a lot of storage, and we're at almost 99% of the hours in a year that are being met by solar and wind alone. We can look at specific weeks and show that we still may have a problem, that 1% is a challenge. And in particular, this is showing that in this system where we have solar coming in and out every day is the yellow here, and wind is in purple, doesn't meet the demand for electricity. And so we have these red hatched areas of unmet demand. And in this case, you see that we have 5 days in a row where a substantial amount of electricity is not being supplied. That's not acceptable to our economy. So we'll have to fill those gaps. And so we've now looked at this similar analysis for other countries around the world. You can see we have a list of countries grouped by continent down here at the bottom. And of course, different latitudes or different size countries have a different optimal mix of solar and wind. So these dots are showing us what the most reliable mix of solar and wind are in these different countries based on their geophysical resources. The top panel is assuming no storage. You see, again, a lot of wind-heavy systems. When you add storage, you consistently get more solar penetration because you're overcoming that nighttime. But even still, places like Russia look like a pretty wind-heavy mix would be ideal given their resources. So I'm not going to spend more time on this, but we've looked at cases of overbuilding as well. So in that same study, what we've done is to look at the gaps. So what we've shown is that you can cover a lot of the hours a year with solar and wind, but when you look at the characteristics of the hours when power demand is not being met, that tells you something about what kind of backup technologies you might need. So in each of these plots, what you're seeing on the y-axis is the fraction of generation in these countries that would need to be supplied for how many hours of the year, assuming some solar and wind-based system. So the 1X are ones where we haven't overbuilt. The 1.5 green lines are ones that we have overbuilt, and then you have different amounts of storage. So, the case where you've overbuilt and you have the most storage means the lowest area under this curve, which is what you need for backup. But it's important to note that maybe 25 to 50% of your entire generating capacity would be necessary for a few hundred hours a year. That actually really defines the challenge, because it shows that if you wanted to do that with something like a lithium ion battery, you're only going to be using it a fraction of the year, but you need a lot of them. 50% of electricity generation is a whole lot. So that's a challenge economically. So just to put it a different way, it means that given the fact that these gaps are large, but they're infrequent, the utilization rate of anything backing up the system is going to be low. And that's why we tend to want to find electricity sources that are going to have low fixed costs. You don't want to build something super expensive and then only use it very rarely. If you are only going to use it very rarely, you want to have it to be cheap and most of the cost associated with running it. That's why, for example, we like natural gas in our current system, is because it's dominated by the cost of the fuel, not the cost of the turbine itself. So what we need is something like a natural gas fired turbine, but without the CO2 emissions. Thinking about energy storage, here again, this plot is showing the cost of different storage in terms of utilization rates. So the left ones, as you move left, you're using these things less and less often during a year. 365 would be something cycling every day. And so you see, as you use something less, the costs per unit of electricity that you're getting from it increase exponentially. And that's why if you're using something like lithium ion, you're going to have a hard time if you're not using it often. It gets very expensive. You know, this is equivalent to close to $1 a kilowatt hour. In contrast, if you're using something like hydrogen, you can cycle it quite a bit less. So now I want to talk about why that might be. So hydrogen is interesting because, and here I'm showing it as PGP, which is what we call a power to gas to power, using electricity to make hydrogen and then using that hydrogen in turn later to make electricity, is attractive because it's dominated by costs of power capacity and not energy capacity. So what I mean by that is that the cost of an electrolyzer is to do with how much hydrogen it can make in a very short amount of time. But when we have the luxury of an entire year, we can buy a relatively low power electrolyzer and generate very large quantities of hydrogen energy that we can use later. So we're only going to be actually burning that hydrogen or putting it in a fuel cell a few hundred hours a year. The rest of the year, the thousands of hours, this small electrolyzer can be generating that fuel. So in this study, we looked at a system that was solar and wind only, and we allowed it access to both lithium ion as well as a power to gas to power storage technology. And we put current costs in and modeled it economically. And what you see is that the lowest cost system uses both lithium ion batteries and hydrogen here on the top, but in very different ways. So over the course of a year, which is the horizontal axis here, we see the batteries are being cycled on a near daily basis to cover you in the evenings, let's say, when solar is not being produced. In contrast, what happens with the hydrogen is very, very different. You see that essentially the hydrogen is building up over the entire winter and spring, and then it gets drawn down in a very short number of weeks during the late summer, during the doldrums of the wind, really. So this is something that's a daily technology when you look at the lithium ion batteries versus a more seasonal setup in the case of the hydrogen. And in fact, when we look at the cost of an entire system that's relying on either solar only in these three bars or wind only or a combination, what we see is that consistently when you add some form of long duration storage, and in particular here it was a hydrogen-based system, you're always going to decrease the cost of the system relative to a system that didn't have that and rather only had lithium ion batteries. And we think this is a very important finding because states like California, for example, that are interested in relying almost entirely on solar and wind have been imagining building a lot of lithium ion batteries to back up that system. Those batteries have a lot of value, but what we're showing is that adding on the capacity to have a longer duration storage technology, perhaps hydrogen, would already make the system cheaper, even at current high electrolyzer costs. And then finally, just to make the point, because I've hit you with hydrogen several times here, not only does hydrogen have this potentially exciting role in long duration storage, but it also would go a long way to helping us integrate the electricity system with transportation. Remember, I mentioned hydrogen in the context of synthetic hydrocarbons, as well as the industrial sectors. So again, I mentioned hydrogen as a potential reductant in the steel industry. This means that we could really use the capital of an electrolyzer constantly to supply different demands in our energy system. And so that's why a lot of people are excited about hydrogen these days, including here at UCI. So the takeaways on this electricity part of the talk are that the geophysical variability of solar and wind resources define the need for some kind of a backup technology if you want reliable electricity. And that may come from a combination of flexible generation sources, demand management, and energy storage. But we know by virtue of the gaps that we probably need to look at systems that are low capital costs or have flexible uses, as I mentioned. And our best economic analyses so far show consistent benefits of long duration storage with hydrogen. So to wrap up, I think, I started out the talk by pointing out that we have tremendous prospects for decarbonizing our energy system in the near term. There's a lot of runway to drive down emissions to very low levels relative to the present. But that said, I think it's already time for academics and business leaders to start seriously contending with some of the remaining challenges. We can't wait until we're 80% reduced in our CO2 emissions to start addressing some of the more difficult pieces of the energy system that I've talked about. And those are different challenges than what we're looking at with electricity generation to the beginning of our decarbonization process, or light duty vehicles. And we really need to coordinate and analyze the potential of different technologies at a system level and in coordination with policymakers and businesses. So that's all I had for you today. And I think I'm at the end of my time, but I did want to at least leave you with a list of the many people who have contributed to the work that I've just talked about. Thank you.
Thanks very much, Steve. That was a great talk. I would like to encourage anybody who has a question, please utilize the Q&A box and you can type it in there and Steve will be able to see it and then we can address it. It looks like we've got a few. So Steve, I'll go ahead and let you read some of these. I think you've got them and you'll answer them as you see fit.
Let me see how to do that. When I present, I can only see a couple people at a time.
Well, why don't I read them to you?
That would be super helpful. Thanks, James.
Yeah, okay. So we have one that says, even though there are high costs for creating energy storage, what's the cost of their upkeep over time and does it have any impacts? That's from Pasha.
Yeah, so that's a good question. And obviously the answer is going to depend on what kind of energy storage you're talking about. We all have some experience with lithium ion batteries and the fact that using them repeatedly, cycling those batteries does degrade those batteries and their performance over time. So there will be some, costs associated with keeping up that system if we're relying on something like batteries. It's a little different when you're talking about pumping water uphill and letting it out through a dam. There's a huge capital expenditure at the outset, but the systems are pretty reliable for many, many years. So yeah, the costs of storage will be a factor going forward, but it's going to depend on what exactly we're talking about.
Thanks, Steve. So we've got a question from Luca here. It says, great talk. What's the most high value chemical that you think we should focus on to produce if we're worried about capturing CO2 from the atmosphere? I know that's not exactly your expertise, but maybe you have some thoughts on what do we need to do towards CO2 capture?
Yeah, it's actually something that we're thinking a lot about. We have another project looking at the potential to make biofuels from seaweed. And I keep coming back to the highest value use of captured carbon like that, I think will be in some of these high energy density liquid fuels for things like aviation. I think those are going to be things that are very difficult to decarbonize in other ways. And so as we become more and more serious about our climate goals, the price of fuels that could meet those demands without adding CO2 to the atmosphere is going to rise. And so that's kind of what I'm looking at. Although I think maybe Luke is getting at other industries like the chemical industry that's trying to make plastics and things, maybe other high value uses there.
Yeah, and I should just mention that we have some chemists who are part of Solutions at Scale that are sort of involved in some of these, and some of them may be on this call now that will circle back with these kind of great questions. There's a question here from David about modern nuclear power plants, maybe next gen nuclear, and how you see that might factor into it. What do you think about that?
Yeah, I mean, I think there's some potential in some of the nuclear technologies that are being presented and demonstrated now. I think in particular, people are excited about the small reactors that could be built sort of at a lower overall capital costs. I think in a way, you have an opposite problem with nuclear than you do with renewables. So something like solar, you're not able to dependably get electricity all the time that you want. With nuclear, where it's a capital intensive generating technology, you really want to operate that as much as you possibly can, and you're loath to turn it down or turn it off. And so it has this problem of it wants to push out solar generation because it wants to be operated all the time for economic reasons. So we need to think about how we can make nuclear more flexible. For example, building a lower capacity plant, but storing some of the electricity it makes is something that people are talking about. But yeah, I think there's potential, and it's a good side topic. Maybe we should have a seminar exclusively about nuclear at some point.
Yeah. And then, so we have Richard Donovan who's asking, can you talk about life cycle costs for batteries? For example, how often do we need to reverse engineer technologies like plastics in order to deal with emissions? I guess the impact on recycling batteries and whether that's possible, et cetera.
Yeah, I mean, it's a fair point, and Richard is an expert on LCA. So thinking about some of those upstream emissions, as I kind of intimated a couple times, just because you have something that itself, when burned, doesn't emit CO2, doesn't mean there was a fossil fuel used upstream to make it or support it in some way. So ideally, as we decarbonize our energy system, there's going to be less and less fossil fuels being used for energy throughout. So some of those life cycle emissions will go down on their own, but it's absolutely imperative that we make sure of that by studying carefully the life cycle and other sources of emissions that may be happening, or other pollution for that matter, during the production of different technologies.
So the next question is from Barbara Sanders, who asks, how does UCI interact with politicians like Rick Perry? I'll just mention anecdotally that Rick Perry was former head of energy for the Trump administration, has actually interacted a fair amount with a spin-off company that came out of physics called TAE Technologies, which is a private fusion company, and has even visited TAE and talking about public-private fusion partnerships. And Steve didn't talk about fusion. But it's sort of an interesting potential technology that if they're successful would play a role in this sort of constant source power piece of the grid. In terms of other politicians, I mean, one of the goals of Solutions That Scale is to create a platform where we can interact more with policymakers, et cetera. Steve, I don't know if you have any comments on that question, but I thought I would at least mention that.
Yeah, I mean, what you said, I fully support. I don't know much about Rick Perry in particular, but we're lucky. A lot of our faculty have contacts and people that they do talk with somewhat regularly in both the business world as well as in politics. And in some cases, some of the research that's gone on has inspired pieces of legislation and different bills. And so there is some connection, but we're hoping to grow that. And that's part of what Solutions That Scale is all about.
Thanks, Steve. So Barbara Finlayson-Pitts asks about the timescale for CO2 capture by cement. Isn't it fairly long compared to the timescale for emissions? And I have a follow-up question on that. And I was wondering about how badly does the cement degrade as it's uptaking the CO2, and does it become less useful in the long run if it does that? So, yeah,
so both excellent questions. So it does take a long time to absorb. And so the recent years that I pointed out that we've had a lot of carbonation going on are by virtue of the fact that we've got decades worth of production of sidewalks and buildings and bridges out there soaking up all this CO2. So it is on the time scale of decades, but there are ideas of how we could manage waste, say post-demolition. Instead of burying cement waste in a landfill, we could try to grind it up and use it for things like road beds or even aggregate to new concrete. and thereby expose new surfaces that would accelerate that uptake process. So that's something we're thinking about. It does affect, as I mentioned, the pH as concrete, cement in particular carbonates, and it can be not good for the structural integrity of things like bridges, James. That said, some uses of cement, it's not necessarily that deleterious, where there's not as much reinforcing metal and structural integrity to worry about, for example. And it actually does harden the cement a little bit. So I think it's one of these things that it's probably a negative, and something that you're at odds with people who want to extend the life of cement, that are trying to put coatings and things, painting, to prevent the access of CO2 to the cement, to prevent the carbonation. From the climate perspective, that's not a good thing.
Interesting. Thanks. I'm going to answer a question that Ted Wright posed, which is, will there be a recording of this talk somewhere? The answer is yes. So this is being recorded, and we're going to put the slides, as long as Steve's okay with it, and the recording of the talk on the Solutions That Scale website. It should be up, I think, within 48 hours. So just check back there, and it should be posted. Let me also mention now, and then we'll move on to more questions. We're going to be doing this kind of talk once a month. And next month in February, we're going to have Martin Powell on February 18th. He's the Chief Sustainability Officer for Siemens Corporation. He's also an author and an engineer. He works with cities to tackle climate change, specifically trying to deliver zero carbon targets for those cities. He's been a special consultant to the C40 Cities Group, which is this group chaired by Michael Bloomberg. He's the former deputy mayor of London. And he brings, I think, a very much sort of world expertise sort of beyond the halls of academia to these kind of discussions. And we look forward to having Martin here with a similar talk next week. So anyway, with that, let's keep answering some questions. So Sabine is asking, Steve, could you speak a little bit more about carbon capture? How far are we with these technologies, and can we employ them at larger scale?
Yeah, I mean, I think that we have successfully demonstrated, companies have, not, when I say we, that's a grand word, but companies have demonstrated the ability to directly capture carbon from the atmosphere, even at its very low concentrations. It's a matter of energy that has to go into that and the cost associated. And so targets, aspirational targets, some would say, of $100 per ton of CO2 captured from the atmosphere right now are common out there in the literature. There's a professor, a former colleague of mine, David Keith, who has his own company called Carbon Engineering that's doing some of this. There's people in Europe, Climeworks, I think is the name of one, that's showing how to do this. So it is out there, it's possible. It's a matter of, is that the most cost-effective way to take the carbon out of the atmosphere and manage the carbon? Or can we actually just avoid the emissions to begin with? And where's the balance?
So Robert is asking, how useful would it be to build and maintain energy storage centers based on seasonal rain, such as turbines that would harness the rainfall, draining out into the ocean in Southern California? Have people thought about that?
I mean, I think that's not so different than when we talk about hydropower in general. I mean, hydroelectricity is using rain and gravity. Unfortunately, if you're talking about doing it here on the coast, you really don't have a lot of elevation. So the amount of energy stored is proportional to the volume of water and the elevation that it's being let down. And so it would be a little bit less interesting than if you had it somewhere up in the mountains where you could store a lot and let it down through multiple dams, for example.
Thanks, Steve. So Melissa is asking about, let's see, it's a little bit of a long question when I get to it quickly. How do you fund these projects with economic feasibility? You've mentioned in the beginning of your talk, the solutions will relate to historical differences of development across the globe. And I assume the goal is to move away from older technologies to newer technologies. How can we help fund these projects in the developing world? And what about political support? how can we generate political support for such a transition? This is an easy question for you, Steve.
Yeah, there's a lot there. That's a career's worth of research. But I think it's a really important point that we often have a very high income economy perspective where we're already in a position of a very robust, reliable electricity system, and we're looking to transition that into a more sustainable one. It's a very different thing than a place where maybe a lot of the population has no access to modern electricity and they're looking to build a sustainable system from scratch. So this is a big topic of interest in the literature, and how to avoid having all of these countries that are now developing going down the path of fossil fuels that places like Europe and the US did. Can we do that in a way that's cost effective to help those people grow their economies and achieve their other goals for their society without emitting CO2? I don't have the answers, unfortunately, but I think it's a really great topic to look into.
Thanks. So we've got a question here from Plowman. This talk targets a scenario of a developed economy, so it piggybacks off the most recent question. Which technologies would be the most important to decarbonize China, India, Brazil, et cetera? So will there be a differential technologies? I think it sort of speaks to the same, broadly the same question.
Yeah, I mean, I think when you think about different countries, as I showed in some of the talk, there's different renewable resources that are available in those places. So obviously, if you have a bunch of one or the other of solar or wind, then you might be interested in pursuing that technology more than the other. Wind tends to be nicely paired with transmission that I've shown, which there are some technologies for doing transmission at large scales with low losses that would be important to pursue. Solar pairs better with storage, so storage is going to be important. But you'd also want to look at what they currently have. I guess piggybacking on the former question, China is still heavily dependent on coal. And so you might be thinking about what are they using that coal for, and what are the technologies that could supplant coal in those different applications. So I think it's a longer conversation. Maybe I should take it offline with Plowman. But
great. So Dan Stokels is asking about ocean energy from waves. Can that play a major role?
Yeah, I mean, I do some back of envelope calculations with my sustainable energy class, and from what we can tell, in most places, wave and tidal energy is a pretty niche potential. It's not to say that it couldn't be economic and useful, but sort of in keeping with the solutions that scale, it's never going to amount to a large fraction of the world's energy demand.
Do you have a sense, this is a question from Ted Wright, how much of the cyclic need for energy can be reduced by demand management, perhaps through pricing?
Yeah, so we have looked a little bit at that, and there's people that have done research on it. There's a lot of potential for cost-effective demand management at relatively short timescales. So, technologies that, for example, would turn off your refrigerator without you knowing for a few minutes. And that can actually be a very useful way to manage the demand and get loads to work out in the grid today. The problem is when I showed that there might be 4 or 5 days in a row that have half of our energy demand is not being met, it's hard to imagine figuring out demands in our energy system that you could turn off that are that substantial for that long. The only things that come to mind are like big industrial activities where the cost of turning that off for 4 days in a row would probably be more than doing something else to cover you for that electricity. So demand management is useful in some settings, but it has limits for sort of the seasonal and larger scales.
Great, thanks, Steve. So we have one final question before we all depart, and I figured maybe we try to squeeze it in. We have one more from Richard, who's asking about cold storage. What are the opportunities for storage in important economic activity like cold storage, where we can store energy by overcooling when renewables are available, or similarly chemical processing like beer when renewables are available?
Yeah, well, I think, one way you can think about the reliability issue is that we know wind and solar are going to vary. The question is, which part of our energy system can bear that variability the cheapest? And we think probably electricity is one of the harder ones. So if it's heating and cooling, or it's making fuels for transportation that you can easily put in a tank as opposed to needing to have electrons stored in a battery, that's probably going to be a cheaper option. So I think cold storage is one that ought to be looked at if we can overcool in the way that Richard suggests.
Great. Well, Steve, we've run out of time. Thank you so much again. This was fantastic. We're going to do this again in a month. And as I said, this will be posted up online. So thanks again.
My pleasure.
And,
thanks, everyone.
Yep. Bye-bye.